So you want a short video? Is that what you're saying? Fine. We start talking about fluids in motion, um, fluid dynamics, and the first part of this we talk about. We say that there's let's take some fluid in an enclosed space. Back up, back up. Well, there's what we call the equation of continuity. All right, and you should be familiar with that terminology. I'll just call it usually continuity. Continuity says basically that mass is conserved. All right, that the mass flow rate of a fluid in an enclosed space is constant. And what that means is, here's a certain in this volume, there's a certain mass of fluid, depending, of course, on the fluid's density. All right, what that says is, really, we can say that mass per unit time, let's call this in area 1, and mass per unit time in area 2 have to be the same thing. The same amount of mass basically gets to a point and leaves a point in the same amount of time, no matter what's true about the enclosure itself. Okay, so we can write this as mass. We can write as rho V1 volume, right, over T equals rho V2 over T. Now again, we are assuming the gas is incompressible, meaning the density doesn't change. All right, so if density is the same everywhere, well, we say that's true. Okay, and we call this, where this is mass flow rate, we call this, if it's volume per unit time, we call it volumetric flow rate. Oops. So we're saying that volumetric flow rate has to be constant, and that might be, I don't know, easier to, or as easy to understand as the mass flow rate thing. This says that if a gallon of water per minute comes into a point, then a gallon per minute must leave that point. Sure, because where the other fluid go. Okay, now we can take this into, well, let's see, the volume of this subsection of fluid, we would say this has area A, and let's call this, like, I don't know, a delta X. All right, so we can say that volume is really A1 delta X1 over T. Well, that's got to be equal to A2 delta X2 over T. Well, over here in area 2, what's that volume of fluid going to look like? Well, since the area gets so much smaller, right, it means that our delta X has to get a lot bigger. Okay? And what you can also tell is if this delta X has to be a lot bigger in the same amount of time, what we're really saying is that there is this relationship, A1V1 is A2V2, right? To pass the same amount of fluid past a point per unit time, well, if the area of that enclosure gets smaller, it means that the fluid has to speed up. Okay, this is what we call the equation of continuity. Okay? We also just define, here's yet another place where we're repeating a variable. We call Q is what we call volumetric flow rate, which you can call volume. All right, I got to be careful in a second here. Let me back up. Now, this delta X over T is velocity, right? These are velocities, very important. Velocity. All right. Notice small v, not volume. Okay. When we talk about this over here, this v is volume. Okay. So we just want to make sure that we define this one quantity that we call Q which is our volumetric flow rate. So it's V, big V. We'll do like this, so it's like a capital V over T, also equal to A times V. All right, so two ways of finding volumetric flow rate, either volume per unit time or area times volume. Sorry, area times velocity. All right, so here's a sample problem with this continuity sort of concept. And it says we have this garden hose, blah, blah, blah. The cross-sectional area is that from which water fills a bucket in 30 seconds. Volume of the bucket is that. Find the speed of the water. Okay, so let's see. To find this, find the speed of the water as it leaves the hose. So if we're going to find speed of water, it's really going to be part, it's going to be this, A times V. So for the hose, we can use A times V. Well, continuity could say A2, V2, bucket. Right? Except we don't know the area of the bucket or the water doesn't flow through the bucket, so it'll be hard to define a velocity there. But what we do know for the bucket is volume of the bucket and how long it takes. Okay? So how about I do this? We'll call this hose, and we'll call this bucket, bucket. Okay, so if we want to find the speed of the water in the hose, we do this. V bucket over area hose times time. All right, that's the volume of the bucket is 8 times 10 to the negative third cubic meters over, let's see, area. Oh yeah, it gives us area, which is nice. 2.85 times 10 to the negative fourth square meters times 30 seconds. Velocity in the hose. Let's see. 883 divided by parentheses 2.85 insert. How do I insert? Clear. So I get 0.936 meters per second. What do you think? Continuity, 8 minutes, 8.5. Yeah, tomorrow we'll work through some continuity problems. I would say the biggest deal, right? We have A1, V1 is A2, V2 with V as velocity. We also have Q is big V over T. I'll do this in a different color. Q is big V over T, where V is volume. All right, just do your best there, folks. It's a pain. All right, and of course we have that Q is equal to both of those things. Okay? Okay. See you tomorrow.